Okay, hello and welcome back everybody. This section is called linear maps and inverse linear maps. And in some way this section serves as a turning point in the semester. We really have kind of three sections to the semester. So before we get into what linear maps and inverse linear maps are, I want to go back to the overarching idea of the semester. Which was basically to analyze and have the ability to solve the Schrodinger equation, right? Which was I, h bar, and then a time derivative of this thing called a quantum state, psi inside of a ket, that was equal to h hat psi inside of a ket. And there's really going to be three ideas to the whole semester. What we've been studying so far is pretty strongly these psi's, okay? Because we've really been analyzing vectors this entire semester so far. And we'll recall that quantum states, such as this psi, are vectors. And to solve the Schrodinger equation, it's to our advantage to decompose these. It's to our advantage to use an orthonormal basis decomposition of psi as, and instead of writing it as, I'll just write it equals the sum, k is in some index set of, this is what's interesting, you write it as psi against psi hat k, and then reconstruct it against psi hat k. So this is exactly your orthonormal basis vectors, also known as pure states, and we still haven't discovered what those are. And this is the quantum superposition. And then we have our inner products, and then we have the current state of the system. And we did cover this a couple videos ago. But I want to remind everybody, I think everybody was becoming maybe a little lost when we were in Taylor series and Fourier series, that whenever our quantum state psi exists over a positive amount of space, then it is a function of space, meaning that psi is equal to psi as a function of x space. But if psi is a function of x, and maybe I'll just write this as f of x, then we need to understand orthonormal basis decompositions of functions themselves to understand quantum mechanics. And what are the two most common orthonormal basis decompositions of functions? The two most common are the Taylor series, where we can decompose. I'll write the function like this now and make it look like a quantum superposition for you. The Taylor series, this would be x minus a center to the nth power over n factorial, and the Fourier series, where psi of x would be a sum from negative infinity to infinity of an integral 1 over 2 pi, the integral minus pi to pi, psi of x e to the minus I n x dx, e to the I n x. So unfortunately, we need these decompositions of functions to be able to handle any sort of quantum state where our state exists over a positive amount of space. And there are certainly cases where they don't exist over a positive amount of space. Spins, for example, spin up and spin down, is not a state-based quantity. It doesn't care where the electron is. It doesn't vary over space. It just has a decided value. So that would be a case where we don't need functions. But another example is just the probability of locating an electron, so a position vector. is going to be a function of space. So the probability of locating an electron 5 feet to my left may be a lot higher than 1 foot to my right, and there's a continuum all the way through. So to handle problems like that, you do need to be able to decompose quantum states into an orthonormal basis decomposition, which is where we've discovered the Taylor and Fourier series from. However, that's really all we've analyzed this entire semester, right? We've only been able to tackle psi. We will spend kind of 2 other sections of the semester. So this is the first section of the semester. We were analyzing vectors and vector spaces. Vectors, vector spaces, and orthonormal basis decompositions. In the second part of the semester, we're moving on to this object H. So second section, we're going to be analyzing H, or H hat. And H hat is technically something called a Hermitian operator, but the word operator is a fancy word for map. And Hermitian is a fancy kind of a linear map. And so really we're spending the entire second section of the book on something called linear maps, which now you can see where that title comes from. The third section, which is going to take us a little while to get to, the third section will be on DDT. We'll be analyzing differential equations. And actually there are definitely parts where both the third and second section do become intertwined. We do handle differential equations before technically getting to the definition of Hermitian. But we'll see how it all goes into play. But basically what I want to think is that we've analyzed psi to our heart's content. We know everything we're going to have to know about psi. Let's move on to H for today, the capital letter H. Okay, so with that said, let's talk about linear maps. Linear maps. And I'm going to write linear maps on vector spaces. They can really only be defined on vector spaces, but I'll just add it in there because why not? So let's give it a definition. A linear map, I'm going to give it the name capital L. This is pretty common in mathematics, even though obviously you should think about this as, oh, this H hat. But we're going to use capital L because that's what the mathematicians use. And we're going to take some vector space and we're going to end up in a new vector space. Okay, so both V and W are vector spaces, but possibly not the same. Possibly not the same vector space. So linear map L, mapping V to W, satisfies the property L against a linear combination. So I'll say A V1 plus B V2 equals a linear combination of the outputs. So this should really be thought of as L on a linear combination is the same as the linear combination of L. So not all maps are going to satisfy this property. Let's look at just one map that does. F of x equals 3x satisfies this, since f of a x1 plus b x2 equals, well, by definition, what does it mean to plug something into to 3x? We're just going to do 3 of a x1 plus b x2, and we know how multiplication behaves. This is the same as 3a x1 plus 3b x2, which is the same as a times 3x1 plus b times 3x2, which is the same as a times f of x1 plus b times f of x2. So this is f of a linear combination. Linear combination. This is a linear combination of f. So the fact that they're equal means f is linear. Let's see an example of a function that's not linear. F of x equals x squared does not satisfy this, since f of ax1 plus bx2. What does it mean to evaluate f on some of these? This is just ax1 plus bx2 squared, which I can FOIL. Well, maybe I'll write it out, make it explicit for everybody, but then FOIL. And when I FOIL here, I'm going to have first, outside, inside, last, and we will end up with ax1 squared, a squared x1 squared, plus ab x1 x2 plus ab x1 x2 plus b squared x2 squared. Or I could rewrite this as a squared x1 squared plus 2ab x1 x2 plus b squared x2 squared. Now the question is this equal to a times f of x1 plus b times f of x2? I don't know, you should stare at this for a moment and try to determine if you think these are equal. It's pretty easy to tell they shouldn't be, because that's a to the first power, that's a to the second power, that's b to the first power, that's b to the second power. The only term that has them both to the first power is the middle term here, but on the bottom they're not multiplied together, so this really doesn't feel like they're equal. Let's just verify that really quick by writing out what af of x1 is. Well, that's a of x1 squared, and bf of x2 is bx2 squared, and now we can really see that this collection of terms is definitely not equal to that collection of terms. Not equal. So not linear. So that's all it means to be linear. Of course, when I write it out in one dimension, things look a little bit too easy. So in reality, it's a little trickier to show. I'll say it's trickier to show that other dimensions have linear maps. Okay, so we need to do this for higher dimensions. Let's look at one example in 3 dimensions. So let's do an example in 3 dimensions. I'll write out that L of x1, x2, x3, there's my 3-dimensional vector. Let's say that this is equal to 3x1 minus 2x3, 2x2 plus x3, and x1 plus x2 plus x3. I'm going to claim L is a linear map. How do I show this? It's not very easy to show this. So what you need to do, I need to do 2 things. First, I need to compute L of a linear combination of vectors. So what is a linear what would A times x as a vector plus b times y as a vector look like? We need to compute that and simplify. Secondarily, I need to compute a of lx plus b of ly and simplify. And then I need to finish by checking to see if 1 equals 2. If yes, then linear. If no, then non-linear. So that's always the process, and it's just a little bit of work to actually go through it. So let's figure out and decide what I even mean by these objects. So let's figure out what a times x as a vector should look like. Well, a is always a scalar. X, because I'm in 3 dimensions, can be written as x1, x2, x3. And because I've got a scalar here, I can distribute it to each entry and arrive at ax1, ax2, ax3. Moreover, b, y as a vector, can be written as b times a vector y1, y2, y3. And I can distribute b to each term of y, and I end up with by1, by2, by3. And finally, there is this addition that's occurring, right? The addition's occurring between these two. So if I added those together, I could end up with ax vector plus by vector. And just add my vectors horizontally, I get ax1 plus by1, ax2 plus by2, ax3 plus by3. So that's okay. I can think of, in step 1 then, I think I can think of 1, instead of having L of A x vector plus B y vector, I can think of L of this nice term that I've just computed, which is AX1 plus BY1, AX2 plus BY2, AX3 plus BY3. And now I need to ask the question, what does this look like? It needs to be computed as something. So my job now, the best way I can place this is that this x1 and that x1 are not the same. Okay? So really what's going to happen here is that the x1 that I started with, the one up here, that's just a placeholder for wherever that goes and wherever that goes. It's a placeholder to say whatever goes in that first entry ends up in 2 places on the right. So let's go ahead and instead of writing it as x1, let's just write it as a nice red square. So this red square, whatever is going inside of the box on the left goes inside of the box on the right. Let's do the same thing with x2. Whatever goes inside of the blue box on the left goes inside of the blue box on the right. And finally, whatever goes inside of the green box, and I realize in the video all these colors are backwards, so I guess we have cyan, yellow, and magenta. Whatever goes inside of the magenta box on the right. But this really helps me because now I know if I put something like AX1 plus BY1 in the red box, I'm just putting AX1 plus BY1 in the red box and AX1 plus BY1 in the red box, and so on. So I really like thinking about my boxes in this way. It really helps me out, even though I used those variables originally. Now I can calculate the output here. What does the output look like? Well, it's 3 times the red box. The red box is this entire term up top. So 3 times the entire term up top, AX1 plus BY1. Should definitely be a plus. And then I have minus 2 times the green box. Where's the green box? The green box is on the bottom. I realize it's the magenta box. Magenta box is on the bottom. So we have 2 times what's on the bottom, which is AX3 plus BY3. And then in the next line, I have 2 times the blue square, which I know is the yellow square. So 2 times the yellow, which is in the middle, 2 times AX2 plus BY2. Then I have plus what was in the magenta square, which is in the bottom row, AX3 plus BY3. And then finally in my bottom row, I'm adding all 3 together. So top, middle, and bottom together. I get AX1 plus BY1 plus AX2 plus BY2 plus AX3 plus BY3. And that's how you evaluate L on all of those inputs. Part of step 1 says, and simplify. So let's go ahead and simplify everything. We can simplify by pulling, it's going to be to my advantage when I simplify to bring all terms with A's together and factor out an A, and all terms with B's together and factor out a B. So if I look at this, I have 3AX1 minus 2AX3. I can simplify that as A, 3x1 minus 2x3. And then I end up with minus plus in B's, I have 3by1 minus 2b3y3. So b3y1 minus 2y3. I can do the same on the next row. The next row in my A's, I have 2ax2 and ax3, so I have an A, 2x2 plus x3. And in B's, I have 2by2 and by3. So b 2y2 plus y3. And finally, in terms of my bottom row, in A's I have ax1, ax2, and ax3, so I have an A, x1 plus x2 plus x3, and I have a b, y1, by2, by3. So that's going to be me calculating L on the linear combination and simplifying. Next, I'm going to want to calculate A times L on x plus b times L on y, and let's recall that x was defined as x1, x2, x3, and y was defined as y1, y2, y3. When I go ahead and calculate these, I can do those with my color codings as well, and I scroll up. There's the x1, x1, x2, x2, and so on, all the way through all of the entries. So what I end up with is an a times 3x1 minus 2x3. I have a 2x2 plus x3, and I have an x1 plus x2 plus x3. The same occurs for b along with the y's. I have a 3y1 minus 2y3. I have a 2y2 plus y3. I have a y1 plus y2 plus y3. If I go ahead and simplify, right, in all these cases I'm supposed to simplify, in that case I'm going to distribute a and b together as well as combine over addition. The result that I'm going to get from doing those two processes is an a against 3x1 minus 2x3, and I'm combining this with the b case, so b 3y1 minus 2y3. I'm going to have an a against 2x2 plus x3 combined with the b case, which is 2y2 plus y3, and finally an a on the x1 plus x2 plus x3 combined with the b on x1 plus x2 plus y1 plus y2 plus y3. So that's me computing and simplifying for step 2. Step 3, I need to compare 1 and 2. And thankfully when I do that here, there's 1 and there's 2, and what do I notice? They're exactly the same. So since these are exactly the same, hence I am linear. So this is how we go through the work for a higher dimensional linear map. It's definitely a lot of work, but it pays off because these are going to be the maps that define quantum mechanics for us. So as long as we go through this sort of work, we can construct quantum mechanics. Let's talk about inverse maps really quick. So inverse linear maps. We're going to recall from algebra that if I have a function f of x equals y, we can find the inverse function by first swapping x and y, and secondly solving for y. A nice example of that, by the way, the name of the inverse function, f inverse of x. An example of this, if we start with f of x equals the square root of x squared minus 1, we have, in step 1, we write x equals the square root of y squared minus 1, and then in step 2, we solve this for y as squaring both sides. X squared is y squared minus 1, which gives me x squared plus 1 equals y squared, which gives me y equals plus or minus the square root x squared plus 1. And we find out that f inverse of x is plus or minus the square root of x squared plus 1. So inverse linear maps are performed the same way they're found the same way, but in higher dimension. So kind of the tricky thing about today's idea with inverse linear maps is the higher dimension. So we have something like, we can find L inverse, so I'll just call that the inverse linear map of L, a linear map, by writing, right? So step 1 is you write the vector x equals L times the vector y, or L of the vector y. It's not really a multiplication yet, but x equals L acting on y as vectors. And then in step 2, you solve for y as a vector. So let's actually see this in action. By the way, solving, this will always be by solving a system of equations. So who doesn't love solving systems of equations? Let's see this in action. So a nice example. Let's consider the linear map, and let's just take it for granted that this is linear. I'm just telling you this. x1 plus x2, x1 minus x2. So there's a linear map. let's find its inverse. So what are we going to do? We're going to go in step 1 and we're going to say, write out x vector equals ly vector. Let's think about what vectors mean in 2 dimensions, right? So I've got 2 dimensions here. My vectors are really going to be x1, x2 equals L, y1, y2. But what is L, y1, y2? We can compute that just based off the definition here. L, y1, y2 will be me plugging in y1 and y2 to the right-hand side. And I end up with y1 plus y2, y1 minus y2. And so in some sense, we can forget about this inside term and just worry about the vector on the right here and say we've got this expression. Let's solve for the vector y, but the vector y is the vector y1, y2. So we'll go ahead and solve this expression for the vector y. And we're going to do that by setting up a system of equations. Set up system of equations. We're just going to look horizontally like we've been doing this whole semester. x1 equals y1 plus y2. x2 equals y1 minus y2. We can use the substitution method. I'll go ahead and solve for y1, which gives me x1 minus y2 is y1. And now that I know what y1 is equal to, I can go ahead and plug that in to the second equation. Plug in y1 to recover that x2 equals x1 minus y2. That was me plugging in y1 minus y2. Or in other words, x2 equals x1 minus 2y2. Or in other words, x2 minus x1 is negative 2y2. And dividing by 2, I recover that y2 is x2 minus x1 divided by negative 2. Now that I know y2, I go up to my expression for y1, and I see that y1 is equal to x1 minus x2 minus x1 divided by negative 2. And if I simplify this, I really have a plus, and I can get rid of the negative sign here. And so I have x1 minus 1/2 x1, so I have a 1/2 x1 there, plus 1/2 x2 there. If I want to simplify my expression for y2, I can as well, just by distributing the negative 2 to the numerator. Both terms in the numerator, I get 1/2 x1 minus 1/2 x2. So the fact that I've solved this for y1 and y2 means that I can construct my inverse map. L inverse of x1, x2 is just the output of y1 and y2. So the output of y1 was 1/2 x1 plus 1/2 x2. The output of y2 is 1/2 x1 minus 1/2 x2. And here is my inverse linear map. So that's how you always solve for those. Let's go through our final property. This is the primary property of linear maps. Linear maps and inverses. We always have that L of L inverse of a vector x is itself, and L inverse of L of a vector x is itself. This in some ways defines what it means to be an inverse. Anyway, that's all I've got for today. I'll see you in the worked examples episode.